Hello class, I'm going to walk through the solutions for week 11. On this first one here, you just had to get common denominators and add together. And I just wanted to illustrate that we had several cases where a fraction plus a whole number. We had a case where to get the least common denominator, you had to adjust both denominators. But the least common denominator was not the product of 6 and 10, right? I didn't aim for 60, I aimed for 30. That's because 6 and 10 are not relatively prime. They have common prime factors. However, in this case here, 6 and 5 were relatively prime, so their LCD is simply their product. And over here, we had two fractions, but only one of them had to be adjusted, right? The LCD of 2 and 8 is 8. Now, just to illustrate, let me take this one here as an example. You don't always have to, you can combine fractions by addition or subtraction with any common denominator. It doesn't have to be the least. So I could have started with 19/8 minus 3/2 and simply done the product of the two denominators, which is 16, and say that's my common denominator. So I'm going to multiply this fraction by 8 over 8, 8 and 8. Some of you are being lazy and writing just a simple times 8. This is not a good idea. Because 3/2 times 8 winds up being 12. It's a different number. You want to multiply the top and the bottom both by 8, so put times 8 and times 8 there, both. Same thing when you reduce. For example, right here, I did a reduction to simpler terms. And I'm seeing a lot of students just put a divide by 2 here like this. But this is not correct notation, because 64/30ths divided by 2 is 32/30ths. You want to, if you're going to reduce the fraction to an equivalent form, you need to put the divide by 2 by each numerator and denominator. All right, so just be mindful of that. A lot of you are making that mistake in writing. It's very confusing to people looking at your work. So anyway, I could get a common denominator of 16, so I'd multiply one fraction by 8 over 8, the other one by 2 over 2. And that would give me 38/16 minus 24/16, which becomes, I can subtract the numerators, which is now 14/16, and then I can reduce this, right? Divide by 2, divide by 2, and that gives me 7/8. So in the end, it doesn't matter whether you got the least common denominator or any old common denominator. And then here, when the two fractions, I was looking for a statement something like this. If the two denominators are the same, then you can just add or subtract the numerators. That's true. A lot of people mention that. But I was looking for you to manipulate the symbols so that they did have the same denominator, so that you can now just add or subtract the new numerators. So I was looking for this as a result. Number 2. So I drew a representation of the time it took Jillian and the time it took Manuel to run a lap. And they each ran a lap, one after the other person. And if all you do is you draw a representation of 2.5 and you draw a representation of this, and then you say your answer is this, then your representations aren't helping build or support your answer. You want to draw, like, how are you using these pictures to be helpful? So here I drew the pictures in terms of fourths, but then I gave a little comment here about, hey, look, if I take those two pieces right there and put them in this blank spot and then join these side by side, you can see just how much is shaded in total, which is 6 1/4 or 25/4. So I was looking for some way that you're using the picture to support this answer. And here I converted everything to seconds, added those together, and then reconverted back to minutes. I'm not going to go over all the details of this. Feel free to pause the video and look it over. This one was interesting. If you try to get a common denominator on these two fractions, everything was in terms of 40ths, which meant a lot of drawing. So I took a slightly different approach. I drew a representation of 3 5/8, which is in red, and then I drew a representation of 1 4/5, and we're comparing these, so subtraction will be the operation we use. And the difference will be what's in blue. Like when you do comparison, it's like saying, hey, what do I have to add to the green to make the red? And that's the blue. And I was able to construct the blue from this diagram without bothering with big hefty common denominators and drawing a whole bunch of 40ths. I could see I could reconstruct the blue by taking this extra 1/5 plus this extra 1 plus this extra 5/8. So I just combined those together. I got common denominators. I didn't put all the little hash marks up in my drawing above, but my drawing, I think, is supporting my answer very well. The difference is 73/40ths, which is 1 33/40 tons. A lot of people drew pictures of the red and green, but didn't use those pictures to help support this answer. They just did this procedure over here, got an answer, and then had two pictures here that were not really helping in the process. It's one thing to, when you model an operation, you need to use your pictures to show how the operation produces the expected result, not just draw pictures of the two numbers that are being operated on, right? I don't want you just to see you draw this and draw this, but then not show how those drawings help you get this answer. Here you can pause the video and look at my figures here. I just converted everything to pounds and compared them, and then converted that comparison back to tons. I'm not going to go over the details of that. Question 4. Some people, it's really good to show the partitioning of this into fifths, showing 5 pieces. When you just have a bar and you draw another bar, and I'm like, oh, is that really 1/5 or is that 1/6? And I'll copy it and see if it looks the right. And so I catch some people in some imprecision. For me, that's taken care of if you clearly show that you're making your best attempt to cut this into 5 equal pieces. Feel free to pause the video and look at the answers in my drawings here. Down here, no group said this the way I was hoping they would. You want to think of when you multiply 7/5 as a multiplier, right? 7/5 times some amount, then you need to start changing the way you think about this. A lot of you just said, hey, that means 1 2/5. You converted this to a mixed number and then thought in mixed number thinking. But I want to help change and improve your thinking so you can see 7/5 of something as doing 1/5 of that thing followed by 7 copies. In other words, you could write this as 7 copies of 1/5 of A, which is a 2-step process. It means first you're going to partition A into 5 equal parts is the first thought, and then iterate and combine 7 of those parts. Think of it as contract and expand. A gets contracted down to 1/5 of A, and then you expand that amount by 7 times. It would be advantageous for all of you to develop that as an instinctive way of thinking about a fractional multiplier as a 2-step process of partitioning followed by iterating. And I didn't see evidence of that in anyone's work, so that's my feedback on that. Number 5, I was looking for that way of thinking in you're doing this with operations. For example, when you see 7/3 times 4, I think of that as 7 copies of 1/3 of 4, and then I do 1/3 of 4 first, and then I do 7 of those, and I get 28/3. A lot of people are just using the algorithms that they've learned, that they just know they have to multiply 7 and 8, and I didn't really take off if that's all you did, because I didn't insist that you draw pictures or explain too much what was going on here. But it's this, in my work, you're going to see that when I have a fractional multiplier, I do break that down into a 2-step process. Now over here, you could do something similar here, because you could say, okay, I'm doing 12 copies of 7/6. Well, 7/6 is 7 copies of 1/6. So if I'm doing 7 copies of 7, or 12 copies of 7 copies of something, then I just have to multiply the 12 and 7 and make an 84 copies of 1/6. And that's, how you get 84/6. I could have done something similar right here. Again, we had these issues where a fraction does reduce to more simple terms. Don't just write divide by 2 like this and then put that answer, because technically that's false. 90 fourths divided by 2 is 45 fourths. If you want to reduce this to an equivalent fraction, then put the divide by 2 symbol in both places. Here, I was looking for I didn't write any words in my solution here because I just planned to say it, but something that explains that the two-step process, when you do a over b times c, then that really means you are doing 1/b of c, which we discovered that that's the same thing as doing c divided by b, or c/b. Or 1/b of c is the same thing as c divided by b, and we've learned earlier that c divided by b is the same thing as c/b. So I could throw one extra step in here and say, okay, well, c/b literally means to do c copies of 1 over b. So notice how 1/b of c becomes c divided by, or becomes c/b, becomes c1/b. So that all these things are equivalent, and we've shown pictures in the past in our notes of why these things are equivalent, and now we just have to multiply the a times c, and then we get a c1/b. So we have a times c 1/b, and that just means a c/b. Something here I could have also have done a little bit more. We know that we're just doing a times c/d, and then we just that just becomes a c/d. Leave that off, and that's just the same thing as writing the fraction that way. So in either case, even when your fraction, when your multipliers are fraction and your multiplicand is not, you really just have to multiply the numerator with the multiplicand and put that over b. And then over here, when you have a whole number multiplier and a multiplicand that's a fraction, you just have to multiply the multiplier with the numerator of the multiplicand. Now these are procedures, of course, you already all know, and several of you were just simply describing that procedure when I asked you to generalize. But when you build mathematical meanings on things that you can think about and understand about partitioning and iterating, I'm not trying to get you, I want you to build a procedure on top of that conceptual understanding. I don't want you just to say, hey, this is the procedure I learned and I'm describing a procedure. That's when math becomes math magic to a student, when you just tell them to do it a certain way and they don't understand why that way works. So I'm pushing you guys a little bit deeper. I don't want just to regurgitate, I don't want you to just regurgitate a formula or a procedure. I want you to say, based on my understanding of these operations, why does this procedure work, essentially? That's what I was hoping for there. Number 6, we had 7 bags and 2 3/5 pounds per bag. We first did the distributive property and got an answer of 18 1/5 pounds. Everyone got the right answer, but it was the imageries that I was not satisfied by, largely. So here I've drawn, there's one copy of 2 3/5, and then I drew 7 copies of it. And then I just put them all back together in such a way, it's clear to see that we have 14 pounds sitting right there. But then all these partial pounds I'm going to reconstitute. So I'm going to take the purple ones here and start filling in the gaps that you see over here and here. Then I take the green and do the same. And when I start trying to reconstruct whole pounds again, you can see we wind up getting 4 extra pounds over here with an extra 1/5. So the total, so this imagery supports that 7 copies of 2 3/5 will wind up being the same thing as 18 1/5. So very often, one image alone isn't adequate. You kind of want to show how that image is manipulated into a new image that supports the answer. And I did a different visual representation for this one. Here we got the answer by converting the mixed number to an improper fraction first. So we're really just doing 7 copies of 13/5. And so I did a number line where I did 13/5 on my number line, and I just did 7 copies of that and saw where that took me. And it took me to a location of 18 1/5. So here's my justification of 7 copies of 13/5 makes 91/5, or 18 1/5. This one here, we had 2 4/5 pounds times $3 per pound. So this was a case where the multiplier was a fraction and the multiplicand was not. And we did first by distributing the 3. So we have 2 pounds at $3 per pound. So here's the first pound, here's the second pound, so that's already $6 for the first 2 pounds. But then we had to figure out 4/5 of a pound would cost how much. Well, each of these little squares in here, each of these was 1/5 of $3, so it's 3/5 dollars. So 4/5 of the pound would be 4 of those put together. So I got my total. I use this imagery to support my total value would be like $3 plus $3 plus 4 times 3/5 of a dollar, and that winds up being 6 plus 12/5, and 12/5 is 2 and 2/5, so that winds up being 8 2/5 dollars, or 42/5 dollars. So here it is, just doing it, more procedurally, but here's a supporting image to help get that answer. Now this one here, nobody got this next drawing in a satisfactory way. I saw a lot of people take this statement, 14/5 times 3, and they drew instead 3 copies of 14/5. But really I need you to try to understand what it means to draw 14/5 copies of 3. Do not invoke the commutative property of multiplication and say, oh, that's too challenging to do 14/5 copies of 3. I'm going to draw 3 copies of 14/5 instead. No, we need to practice fractional multipliers and what that means. So here we were supposed to combine the mixed number into a improper fraction. So we're trying to do 14/5 copies of 3. So I'm going to do that as a 2-step process. I start with the 3, which corresponds to 1 pound. So here's our $3. I'm going to do 1/5 of that to correspond to 1/5 of a pound. So I first contract $3 down to 3/5 dollars. But then I need to do 14 copies of what I have highlighted right now. And when you do 14 copies of that, you wind up seeing that you get 2 full pounds and then 4/5 of a pound reconstituted. But the amount of money that you see here is going to be $8 and 2/5, $8 and 2/5 dollars, or 14 times 3, which is 14 times 3 is 42/5 dollars. But this imagery here is how you show how you start with $3, which is the multiplicand corresponding to 1 pound, and you first contract it by doing 1/5 of it, and then you do 14 copies of that 1/5 and see how much money you're looking at here. I also simultaneously kept track of the weight, but it was really the money that I was after. How much did it cost? And number 8, a lot of people did not explain this in a way that I felt was satisfactory. In fact, I don't think any group really did entirely. I did say up here, assume A is a positive amount. So some people were saying A is 0, A is negative. No. A is positive amount. And I did say that it could be whole or non-whole. Some people, I think, were only thinking whole numbers, so the A was 1, 2, 3, 4, etc. only. But in general, if A is less than 1 but still positive, then A times 5 will be less than 5. And you're only really comparing the product and the multiplicand. Well, this is the product and this is the multiplicand. Doesn't make sense to compare the multiplier and the product, right? For the reason up here. How do you compare 3 containers and 12 gallons? Like, they're not really comparable if you want to. It's like saying what's more, 3 hours or 2 miles, or what's more, 3 hours or 2,000 miles. It's like, how do I compare time and distance? So when I write a multiplicative statement, this stands for a product, and I can only really compare it to the multiplicand, which is the second number, the 5. You guys need, I think some people were thinking commutative idea and thinking that maybe A was the thing you want to compare to the product. But anyway, if the multiplier is less than 1, like a half, and a half times 5 will produce a product that's less than 5. How about 5 times A? Well, 5 times A always be more than A, and we're comparing to A, to the multiplicand. And yes, 5 times A means 5 copies of A, so it's A plus A plus A. That's certainly going to be more than just A, like, even if A is a fraction. It doesn't matter what A is. When you do 5 of them, put them together, you have something that's more than just A. And then down here, when the student says that multiplication makes bigger, that student probably is coming to that conclusion after working with whole numbers only. And once they start working with the fractions, they need to discontinue thinking that way. It becomes an an intuition that's embedded that no longer serves them well. And so multiplication of two positive numbers, here's how I wrote it. Multiplication of two positive numbers only produces products that are larger than the multiplicand when the multiplier is more than 1. Right? Remember, we're only really comparing product and multiplicand. And the product will be larger than the multiplicand when the multiplier is more than 1. When it's less than 1, then you're going to get smaller products. That is, products that are smaller than the multiplicand. You have to be very precise when you're talking about comparing the numbers involved in a multiplication statement. Conceptually, we only really compare products and multiplicands. And when you just say, hey, this number is more than that number, or you get a bigger number, and I'm like, a bigger number than what? What are you comparing the number to? You have to be very precise when you're comparing, when you say number compared to number, but there's 3 numbers to think about. So use the terms multiplier, multiplicand, and product to your advantage. Don't just say number. And that's it.